Hi, welcome to Chapter 13, Overview Part 3, where we're going to talk about colligative properties. So colligative properties depend only on the quantity, not the identity of your solute particles. Some colligative properties are vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. So let's talk about vapor pressure first. Remember, vapor pressure is when you have a liquid and some of it goes into the gas phase, and in a sealed container, so you have your liquid, some of it will go into the gas phase. So if it's a sealed container, this gas will kind of bounce around and apply a pressure to the liquid. So your vapor pressure is the amount of pressure that the vaporized liquid is pushing, okay? So because of your solute and solvent interactions, or your intermolecular force attractions, the higher concentration of your non-volatile solute will make it harder for your solvent to evaporate or vaporize. So it makes it harder to vaporize. So because of that, it actually lowers the vapor pressure. So if you look at this diagram, you have a pure solvent. There's nothing blocking the way. These molecules could jump into the gas phase very easily, okay? Then you add some solute. They kind of block the path. So say I'm this gas molecule. I have to go around this solute before I can go into the gas phase. So that actually makes it harder for me to jump into the gas phase. So if you look here, once you're at equilibrium, there are less gas molecules over here because you have lowered your vapor pressure. So there is a law that explains this, and it's called Raoult's law. The vapor pressure of a volatile solvent, so your solvent has to be volatile, which means it wants to vaporize, over the solution is the product of the mole fraction, remember we learned low mole fraction in the last video, of the solvent times the vapor pressure of the pure solvent. So here you have the pressure of your solution will be the mole fraction of the solvent times the pure vapor pressure of the solvent. Okay, in ideal solutions, it is assumed that each substance will follow this law. Okay, and note, for your mole fraction, you want the solvent. So your mole fraction for the solvent will be the moles of the solvent over moles of solution. So let's just talk a little bit more about, on the molecular level, what colligative properties are. So here's colligative properties for electrolytes. Remember, electrolytes will separate into ions. Since colligative properties depend on the number of particles dissolved, when you have an electrolyte solution, you will actually get a greater change than a non-electrolyte. And you'll get a greater change because you form ions. So if you look here, here's your sodium chloride separating into ions. Once all of this dissolves, you'll have twice as many particles in your solution. Here is your non-electrolyte, and it doesn't separate into particles. So every one you add is just one. So, however, 1 mole of solution of sodium chloride doesn't show exactly twice the change in the freezing point. So sodium chloride, we would assume, separates into Na plus and Cl minus. So that's 2 ions. Okay? So in an ideal situation, we should have twice as many particles. But in reality, this does not exactly happen, and let's see why. So we have something called the Van Hof Factor, which is this letter I. So we always assume that sodium chloride would produce 2 ions. But 1 mole of sodium chloride in water does not always give rise to 2 moles of ions. And why is that? Well, because these ions are very attracted to each other. And if they come close to each other, they will rebond and now reduce the number of particles. So some of the Na plus and Cl minus reassociate, so they stick together. for a short time. So the true concentration of particles is somewhat less than 2. It is greater than 1, but somewhat less than 2. So somewhere in the range there. So since reassociation is more likely at higher concentrations, you're going to get more deviation. Therefore, the number of particles is concentration dependent. So if you look at this example here, let's just take sodium chloride. Okay, our ideal case is 2 when it's completely dissociating. But as you see, as the concentration increases, this number gets less and less because there's a greater chance of the sodium ion and chlorine ion reassociating with each other. We call our ideal situation the limiting value. The limiting value is what you would expect if there was no reassociation. And in most problems, if they don't actually state the Van Hof factor, you're going to assume it's the limiting factor. It's the limiting value. So how do these particles affect your boiling point and freezing point? So your boiling point will be elevated and your freezing point would be depressed. So a non-volatile solute-solvent interaction always causes the solution to have a higher boiling point and a lower freezing point than the pure substance. And why is that? So if you look at our phase diagram, the dark black lines is the original phase diagram. Once you add some solute, the blue line here is your solution. And you see what happens is now it's pushing everything. So it's elevating the boiling point. It's pushing it down. But it's depressing the freezing point. Why is that? So let's look at the boiling point elevation. Since the vapor pressures are lowered when you add a solute, it requires a higher temperature to reach your atmospheric pressure. Hence, the boiling point is raised. So if you look here at normal pressure, this would be your normal boiling point. Then you add some solute, and the boiling point gets raised. The construction of the phase diagram for a solution demonstrates that the freezing point is lowered. And the reason why the freezing point is lowered is because now your solute particles get in the way. What do I mean by that? In order for you to freeze, you need your solvent particles to become very close to each other. But so like let's say here's our solvent. And here's our solute in the middle. We want to freeze, so these two guys want to get as close to each other as possible, but this guy's in the way. So you have to actually go to even colder temperatures to kind of freeze it in place. So how do we characterize this boiling point elevation? Well, the change in boiling point is proportional to the molality. That's why we learned molality in the last video. So this here is your change in boiling temperature. I is your Van Hof factor. Van Hof. KB is a constant depending on the solvent. This depends on the solvent. And M is your molality. So here is a table of KBs for different solvents. Most of the time we're going to be dealing with water. To get the new boiling temperature, once you calculate delta T, so say we're dealing with water, you take the old boiling temperature and you add delta TB to it, and that gives you your elevated boiling temperature. The freezing point depression, the equation looks very similar except we have F for freezing and we have a negative sign. The negative sign is in there because we're depressing the freezing point. Okay? So, again, most of the time we're going to be using water as our solvent, and this would be our KF value for that. Once you calculate your delta F, it will actually be negative. So if you want to get your new freezing point, water freezes at 0, you're going to do 0 plus delta TF, and you're going to get a your new freezing point. But remember, TF is a negative number. So your new freezing point will actually be negative. So even though you're adding it, because it's a negative value, it's like subtracting it almost. Note that in both equations, delta T does not depend on what the solute is. We never even say what we're dissolving, right? It just depends on how many particles. All right, and this freezing point depression we use every winter when you put rock salt on roads, because you want to have the temperature that the water will freeze on the roads lower, so it has to actually get even colder before you get ice on the roads. So this lowers the freezing point of water, so you don't get ice on the roads. Osmosis is another colligative property, and you probably learned about osmosis in biology. So some substances form a semi-permeable membrane, which allows some small particles to pass through but blocks the larger particles. So in this diagram here is your membrane. Okay, the net movement of solvent molecules from the solution goes from low to high concentration of solute across the semi-permeable membrane is called osmosis. So if you look here you have a high concentration of solvent, and here you have a low concentration of solvent. So what's going to happen? The solvent is going to move across the membrane, and that's what's showing here. See, the liquid level goes down. Then the pressure you have to apply here to get the two liquid levels to be equal is your osmotic pressure. Okay, it likes to flow from high to low for the solvent. So in biological systems, most of your semi-permeable membranes will allow water to pass through, but the solutes are not free to do so. So this is like when we were talking about cells and saltwater solutions in cells in bio. It's also why when you drink salt water, you get actually dehydrated more, right? So here's another picture of it. Here's your membrane. Here's your concentrated solution. It's going to move into the dilute. And then you have to apply pressure to get the two back. So in osmosis, there is a net movement of solvent from the higher solvent concentration, or if you want to think of it as solute, the low solute concentration, to the area of low or solvent concentration or high solute concentration. And here's the equation for osmotic pressure, where this is osmotic pressure. And then you have the Van Hof factor. N is moles, V is volume, R is the gas constant, T is temperature. So N over V is just molarity, so you have I times the molarity RT. If two solutions are separated by the semi-permeable membrane, they have the same osmotic pressure, then no osmosis will occur. You need to have different pressures for osmosis to occur. And that is the end of part 3.